Yeah, thank you. So yeah, I'll talk about some work that I did with Anna Brandenberger, a fellow PhD student, and two undergrads, Nathan Sheffield and Divya Shamil, all at MIT. So the two undergrads, Nathan and Divya, particularly like kind of having a story to motivate their math. So I'll use one of their stories to kind of present the problem. So suppose you have N candidates for, or N employees for a job, and you have kind of N jobs for them to fill. And these jobs are split into two different types. In this case, I guess, front end and back end software. And the twist, I guess, is that you also have two kinds of candidates. So I guess experienced versus inexperienced. And they have kind of different likelihoods of being able to perform each task. So you want to be able to kind of pair up the candidates and the jobs as well as you can. So let's say the first guy comes in and he's able to perform these three jobs, and you pick one for him, and so on and so forth. And so the way we should interpret this is each of the employees is a vertex, and each of the jobs is a vertex. And you're drawing a random graph between these vertices. And so the question is finding as large of a matching as possible in this bipartite graph. Okay. And so
is this online?
Both. You'll see. I'll get into it in the next few slides. Yeah, so I guess the more classically studied case is when you kind of ignore all of these different types, and you just draw each edge in kind of independently with the same probability. This is known as, I guess, the bipartite Erdős-Renyi random graph. And there's kind of results about what kinds of sizes of matchings you can achieve both online and offline in this case that I'll mention kind of later on in the talk. But the twist that we put on it, these kinds of different groups of people and different groups of jobs can be captured by what's known as the stochastic block model, or inhomogeneous random graph, as mentioned. Yeah. Yeah, so this will be right here. Yeah. So the stochastic block model is parameterized by, so Q here is the number of groups, so 2 on each side in the case, in the story I just explained. And M is a matrix of kind of connection probabilities, which is, so these 5 over n and 1 over n that you were mentioning. So these are the probabilities that you connect between various different groups. And so we're interested in particularly the case where these probabilities are of order 1 over n, because this turns out to be kind of where you get matchings of interesting sizes. Okay, so going back to the initial question, we'll first look at the online matching case. So what does this mean? As explained kind of in the story, I kind of gave each of the employees a sequential order. So they came in one by one, and I had to assign them a job kind of on the spot without knowing what happens in the future. So this is what is known as online matching. So at each step, I see kind of a vertex on one side of the graph. I see which neighbors it has on the kind of other side of the bipartition. I have to choose a neighbor to match it to before I see kind of the rest of the graph. And so we want to kind of, yes.
You don't know the rest of the graph, but you know how many vertices there will be in total.
Yes. You know how many there will be, and in particular, you know how many of each type are on the other side. Yeah. So your goal is to kind of maximize the number of successful matches. And a natural quantitative version of this is what is known as the competitive ratio. So you kind of compare how well you can do online versus how well you do offline. Because naturally, if your graph is kind of adversarial and you don't have a big matching in the first place, you won't be able to find a big matching online either. Okay. So in the case of the Erdős-Renyi graph, there's kind of been, this question has been studied, particularly by Maston and Jailet. I'm sorry if I butcher names, but so they showed that essentially the greedy algorithm is the best you can do. So at each step, a vertex comes, it has some neighbors, and you just pick one of them to connect it to. And this is essentially because of all the symmetry, like there's no difference between any of the neighbors, so you just kind of pick one at random. So a natural starting point for us was to see how well the greedy algorithm does in our new setting. And it turns out that there's kind of a nice case where it's still the best possible thing you can do, which is when all of your different classes have the same expected degree. And we called this equitable. So it's kind of for the same reason as in the Erdős-Renyi case, where you kind of want to be matching to all of the different groups at roughly the same rate. And the greedy algorithm achieves this. Okay, so this kind of expected matching size is the same as in an Erdős-Renyi graph with average degree C. And maybe just a quick word about how this is proved. You kind of keep track of some various statistics about how many vertices are left and how many are matched. And these are well approximated by some differential equations. And if you solve these kind of differential equations, you get this kind of weird looking value here. Okay, but kind of the goal of this project at the beginning was to say, well, now we have some extra information about the graph. We know there's some kind of hidden structure or inhomogeneities to the edges. And we want to know whether or not this can help us in our matching task. So I guess we showed that in the case where all the degrees are the same, this extra information doesn't actually help us at all. But there's also bad cases. For example, where we just have one type of employee and two types of jobs, and they're all more likely to kind of be able to do these kind of blue jobs. So the kind of heuristic you should think about here is that if you see an employee come in and he has a red edge, you should want to choose it more because that red job is less likely to be filled by employees in the future. So this motivates the next kind of idea that we had, which is to try and match the jobs that have the smaller average degree. And this was given the clever name degreedy. And so it's also some sort of greedy algorithm, just weighted by the expected degree. And this does, we're able to show that this does fix the problem, specifically when you have kind of only one type of job candidate, so one vertex class on the left. And so this is also maybe not so satisfying because this is still far from a very general class of block models. And so, for example, one issue that we found is this relatively simple case, where now we have kind of two classes on each side and with these kind of connection probabilities. And so there's kind of a competing dynamic here where the red jobs have smaller average degree. And so this degreedy algorithm will want to match the red more. But in reality, you can see that the kind of the second type of candidate has no chance of being able to perform or having a blue edge. And so you should kind of imagine that if you see a blue edge, you should probably want to take this as well, because if you match kind of a top candidate with a red edge, then you're only taking up like matching like possibilities for the lower candidates. Okay, so this suggests that we kind of maybe had too naive of a heuristic in the first case. So we try to take a more holistic approach to our greedy algorithm. So in what we call short-sighted is we just try to, when your candidate comes in and you see the edges, you pick the kind of job that maximizes the probability of the next candidate having options to be matched to. So this is maybe a more general strategy, a more holistic strategy, trying to say that we take into account what's happening at the next step. And so this seemed quite good to us. We were pretty happy with this idea and how it performed kind of empirically. So it does quite well in this kind of equitable case, and it seemed to do well in various other simulations. But we also ran into kind of a curious case, which is very similar to the previous one, where, so again, we have kind of these two classes on both sides with these similar looking connection probabilities. And again, so here we found that this short-sighted algorithm achieves some matching of approximately this size, 0.57. And we found like kind of an ad hoc algorithm that can do just a little bit better. And I'll kind of explain where this comes from in a little bit. But the kind of picture you should have in mind here is, again, there's these two competing kind of forces. So you want to match red edges because they appear less likely. But you want to match to blue because you don't want to kind of take up all the red vertices for the kind of candidates at the bottom. And so what happens when you run this kind of short-sighted algorithm is it will kind of prefer to match to blue. It will prefer matching blue edges up until a certain point, and then it will prefer matching red edges. And what's kind of curious is it actually kind of gets the transition point wrong. Wrong meaning like you can do better by kind of just hard coding in a transition point. And so this was kind of curious. And well, the way we found this kind of 88% is there's kind of a very straightforward thing you can do, which is to try to just look at kind of the trajectory of all possible candidates that can come in and matches that you can make. And you kind of pre-compute all of the expected outcomes. And this brute force way lets you kind of pick the maximum expected, like your maximum expected option at each step. And so what we figured out was that this kind of brute force algorithm essentially does this the same thing as this short-sighted, but it just prefers blue jobs up until a later point. And it does slightly better in this case. And so one of the questions that I guess remains from our investigation was that we found that this short-sighted algorithm does quite well in a lot of cases, but it's clearly not the optimal algorithm as there's an example. But we were wondering if there was kind of a nice way to analyze it to show that maybe it does do kind of provably well in most cases. This is something we couldn't get our hands on, but it would be interesting to figure out what's exactly going on here. Okay, and yeah, this is just a quick note that this kind of brute force approach is expensive and also not kind of easy to analyze exactly the matching size that you get out of it, but it's kind of the best thing you can do almost by definition. Okay, so that's the fairly complete picture of what we found in the online matching case. Again, so some curious kind of behaviors that didn't really appear in the Erdős-Renyi setting just because of all the symmetry. Okay.
Could I ask about the brute force? Is this
Yeah.
deterministic?
Yeah, so like you can look at kind of, you essentially just pre-compute the best possible, like the expected matching size of every possible decision at your current state, and you just choose the maximum one. So yeah, it is like a deterministic decision tree kind of thing to do.
It's obvious that that's the best.
In some sense, yes. In some sense, no, I guess. I think it ends up being the best you can do just because you can look at any particular state and say, well, this is exactly the maximizing path that you can take. So I guess intuitively it's obvious, maybe rigorously not as obvious, but I think this should be the best you can do. Okay, so this, if you remember, this expected competitive ratio is a ratio between kind of online match, the output of your online matching algorithm and the biggest possible matching in your graph. So we also took a look at how big of a matching you expect in general in these kind of block model settings. And here again, in the Erdős-Renyi case, there's this well-known algorithm of Karp and Sipser that kind of achieves it. It's an algorithm, but it outputs a matching that's kind of within, it's very close to the maximum possible. So I'll give you kind of a quick overview of how it works. It's a pretty natural algorithm. So when you're matching vertices and you see a vertex with degree 1, then you should want to match it because there's only one possible option and it might disappear later. So what you do is you just pick a vertex of degree 1, you match it to its neighbor, and you delete both from the graph. And then you repeat this until you're left with only isolated vertices or a component of minimum degree 2, also known as the Karp-Sipser core of the graph. And at this point, you can just start just taking edges from the core and until you're left with no edges left to match. Okay, so Karp and Sipser kind of analyzed this algorithm and gave these two nice results. So they proved that with high probability, it constructs a matching that's kind of little o(n) off from the biggest matching in the graph. And this little n is meaningful because the maximum matching is of order n in this setting. And so they proved this by I think one of the earlier applications of kind of relating Markov chains to a system of ODEs. So you can kind of keep track of how many vertices of various degrees there are, and you can write down the transition probabilities at each step of your algorithm. And they analyze this kind of as a system of differential equations, and they can tell you roughly how big of a matching you get. And something that kind of pops out of this analysis is this Karp-Sipser core. There's kind of a nice phase transition that happens with how big this core is. So kind of as a consequence of their analysis, they show that if your edge probability is less than E/n, so what they call a subcritical phase, then your core is of size little n, and which means you can kind of essentially just ignore it because it's a negligible fraction of your graph. On the other hand, if your edge probability is bigger than E/n, then you're left with some linear fraction of vertices, and you actually have to say something about the rest of the graph. So we also took a look at this same Karp-Sipser algorithm in the case of block models, and we can show some partial results again. So again, in the case of an equitable block model, which if you recall means that all of the edge probabilities of all the different groups is the same, we can kind of modify their arguments in a relatively straightforward way and show that you get essentially the same result. So again, in an equitable block model, in terms of matchings, it behaves essentially like an Erdős-Rényi graph. But again, once you exit this kind of equitable setting, you get some weird behaviors, and it's not so clear what happens in complete generality. And I'll maybe describe some examples in a little bit. And again, something similar happens with this phase transition. So now you have, I guess, not a single parameter. Now you have some matrix of parameters. So it's much more complicated just in terms of dimensionality, but we can show that whenever all of your, the average degree of all of your classes is less than E, you have this same kind of little o and little vanishing fraction of your graph left after removing all the degree 1 vertices. And again, it's not so clear, the picture is not so clear of what this phase transition looks like because of all the parameters that you have. And I'll also give an example in a little bit that would be interesting to know more about. Okay, so as I said, the Karp-Sipser does well when all your average degrees look the same. But here's a case where it might not do so well. So it's kind of a 4-partite graph, and you have sparser edge probabilities on the 2 sides and some dense component in the middle. And what you would likely want to do if you want to form a big matching is try to match as many edges as possible on the outside and then fill in the rest with this dense part. But what Karp-Sipser does is, if you recall, it kind of, at some point, it starts just sampling edges uniformly at random from the core of your graph. And what's going to happen is it's going to start taking a lot of edges from the middle. So you're going to start matching a lot of these kind of middle 2 columns of the vertices to each other. And you're not going to be left with many edges or many vertices to match from the outside 2 columns. And so this kind of motivates natural kind of adjustment to Karp-Sipser, which we called label-aware Karp-Sipser, which I didn't write on the slide, but in words, it's roughly saying when you choose edges uniformly at random, you should instead choose them uniformly at random, but weighted by kind of the degrees of the 2 labels on its endpoints. And we had some thoughts about how this might be something good to do in general, but again, this system of ODEs turns out to be too hard to get our hands on at this point. Okay, and in terms of the phase transition, as I mentioned in the Erdős-Rényi case, if your average degree is less than E, then you're left with some vanishing fraction of the graph. Whereas if it's bigger than E, you're left with some linear fraction. And here's another kind of curious example. So, oh, I guess I forgot to write the edge probabilities, but you should think of the blue edges as appearing with probability roughly 3/n, and the same with the red edges. So this is, I guess, a bipartite graph where you put some Erdős-Rényi graph inside one of the bipartitions. And so it has average degree bigger than E everywhere. But it turns out that if you kind of work through our proof of the subcritical case, that in this setting, when you perform this Karp-Sipser algorithm and remove degree 1 vertices, you'll only be left with a vanishing fraction of the graph left at the end of this process. Which again is kind of curious because you started with kind of a setting where all of your degrees are larger than the previous kind of phase transition in the homogeneous case. And so our best guess as to why this might happen is there's, again, kind of 2 competing, or I guess not competing, but kind of cooperative forces in this case, where you start removing degree 1 vertices from, say, one side, and this kind of reduces the average degree of the other side in some way that lets you kind of continue this back and forth process. but it's really unclear to us why this case turns out to happen and what's the general kind of situation is with this kind of what they call the E phenomenon phase transition with this Karp-Sipser core. So I guess to finish, here are some of the kind of things that I mentioned throughout the talk and that are left that we would kind of be curious to know. So this kind of critical threshold of the phase transition between a linear and a sublinear size Karp-Sipser core. This label-aware Karp-Sipser algorithm that I mentioned earlier, is there a way to kind of analyze this and show that maybe it does well in some settings that the vanilla Karp-Sipser does not? And I guess, is there a way to get your hands on this short-sighted algorithm and really show that it's doing something good that like is supported in our kind of empirical experiments? So that's all I have to say. Thank you.
Thank you. Comments, questions? Question.
Yeah, I was just wondering about the question of getting a more efficient algorithm that gets you to first order the right behavior.
Mm-hmm.
So if you think,
yeah,
You've basically you've got, let's say, Q classes on the left and Q on the right.
Mm-hmm.
You've really got like Q times 2 to the Q types of vertex on the left, because you've got the Q classes and you know who they're allowed to join. So it seems like we could just set up a kind of max flow problem from that number of classes on the left with the classes on the right, and everything is predictable to first order in terms of how many vertices you're going to have in each.
Mm-hmm.
Is that something that could get you the right first order behavior?
I'm not sure. That's an interesting idea. I don't have a good sense of what that would get you, but it certainly seems like a reasonable thing to try. Yeah. Yeah. Yeah, I'm not so familiar with some of this max flow stuff, so maybe we can talk about that later.
Other comments? Yeah, just maximize the like
Now, I guess this is the question. If I understood it, you look here on the say, square page where you have the chain number of the
Yeah.
have you looked at extensions when you have different now?
I think a lot of the things we did would probably still work out. But I don't think we looked explicitly into whether or not that would make a big difference. No. Yeah. Maybe just, so I think we did consider having different size classes, which you could interpret as like if you have different size classes, you can kind of interpret this as having different numbers in some sense.
Yeah, I have a more general question.
Mm-hmm.
You know what that
I don't, but I believe it might follow from what they do in their paper. So I'm not completely sure on this, but so they gave some like necessary and sufficient condition based on some branching process game, and if I remember correctly, I think what they do kind of handles the case where the edge probability is exactly over n, but don't take my word for that. Yeah.
This was actually something that done very recently. So not quite the Hermitian, but you get some quite strange getting, I think it's end of the 3/5. This was projection a while ago, but it was proved recently by the coming out. And they proved that instead for a model where you have, I think it should be possible to do it in the same model. But
Other comments? Well, thank you very much.
Thank you.